First of all, just let me introduce myself. My name's Bernie Davis, and I'm a London-based TV lighting director. And I'm also chairman of the Society of Television Lighting and Design. So it was last year, David Morphy at Cirro-Lite offered us an online presentation on the subject of the advance in LED technology, which we were very pleased to take. It took a little while. We both found ourselves surprisingly busy in the autumn, but at last it's come together. And through the magic of Zoom, we were able to extend this offer to our student network and to other societies, including the GTC and the ALD, and through Kino Flo to a large network of gaffers and DOPs. So this has ended up as a truly international event. So I'm delighted so many people have been able to join us. It's already over 100, and maybe a few more to turn up late, so we'll be watching out for that. One person I would like to welcome in particular is John Watt. John is a past chair of the STLD and also has been chairman of Show-Lite for a number of occasions. So it's not only an excuse to welcome John, but also an excuse for a shameless plug for Show-Lite, which if you haven't heard of is I think it's one of the best lighting events, lighting conferences that happens. It should have been happening this May, but had to be postponed for obvious reasons. But quite soon they'll be announcing that there'll be a virtual Show-Lite this year, a one-day event. So I recommend, if you enjoy talks like this, the virtual Show-Lite should be very good with a selection of papers, and it might even give you a taste for the real one when it comes around. Now, before we get started, just a bit of housekeeping. Frida would like your questions. It will encourage more of a conversational style, which should be a good thing. We just have to be a little careful of that it doesn't descend into chaos. So if you could stay muted most of the time, just for those moments when other noises will break into the sound. But if you want to ask a question, you can unmute and ask it. And sometimes it might be better to interrupt the talk, because there'll be a lot of slides in this, and while the slides are up, it's a good time to talk about it rather than have to try and find them at the end. You can also put questions in the chat section of Zoom, so we'll be trying to keep an eye on that. There's also a feature in Zoom where you can put your hand up should you choose to, and again we'll be trying to keep an eye on that. With so many people, apologies if that doesn't work, but that's what we'll be attempting to do as we go along. Otherwise, there will also be questions and answers at the end. So, as I say, this is a truly international meeting, and how appropriate for a man whose success has been seen around the world. Back in the 80s, Frieder Hochheim was a gaffer in LA who knocked up a light source that he saw a need for, making a robust, lightweight soft light with high standards of light using fluorescent tubes with good phosphors. It was an immediate success, but as I understand, it took the sound man to tell him to start manufacturing them, otherwise he would, and so the Kino Flo was born. And in recent years, he's continued with the march of LED lights as sources. Frieder's been looking into the use of these and how they work with film, which I can tell you from my own experience makes a good story. So let me hand over now to Frieder Hochheim.
Thank you very much, Bernie. First of all, I'd like to thank you, the Society of Television Lighting Directors, for this wonderful opportunity to present sort of the ideas and some of the work that we've been doing. This is going to be a very geeky, a very highly technical presentation, a lot of graphs, a lot of data. Like I said, it's best if you can also use your little in the bottom of your scroll on the bottom of the bar. There's a reactions button, and if you open that, you can also raise your hand if you have a question, and that means that I hope to be able to see it, or whoever's hosting right now. I think Bernie, are you still the host, or is Alexander the host?
No, I assigned you. You are right now the host, but you give it back to me. You give it back to me.
Being interrupted is fine. So, and I'll try to answer as many questions as I can, and go from there. So that being said, first of all, a COVID welcome from Los Angeles. It's a overcast day here, And yeah, we're all in this together. So this presentation I've been doing now internationally for about 2 years, and it's grown out of trying to wrap our heads around what it is about LEDs that we find so frustrating. So let me share my screen here. And also when you, depending on how your screen is set up, in the upper right-hand corner, there are a number of little icons, which are your display, which show the speakers or potential speakers. You can minimize that because my screen will be showing a lot of data up into the upper right-hand corner as well. So in this presentation, I'm going to talk about understanding spectral response differences in camera. We're going to talk about color gamut, not just on cameras, but on other devices and how they influence each other. Talk about white spectrum differences. What exactly, when we say white light, what does that mean? We're going to talk about the challenges of color matching between manufacturers of lighting, how to use gamut and XY in matching gel colors. We'll talk about the use of camera profiles, something that we've incorporated into our product now, and talk about how to account for some of these differences in camera response. Now, Jeff Boyle from the CML website did a wonderful test, which I want to show here. And this grows out of the whole notion when we think of, cinema cameras. The one constant that we have in the world is tungsten. At least you would think so. No matter what part of the world we're in, whether we're in Beijing, whether in Tokyo, London, LA, tungsten should be that one norm that as a camera manufacturer, you think you should be able to balance to. So Jeff went ahead and said, let's just get a number of cameras, balance them to the preset on the camera for tungsten, and let's photograph tungsten. Then we want to back it up with an alternate shot, which is an LED. At this point, it's irrelevant which LED it is, but it is a very common product that's on the market. Also tuned into the same Kelvin as the tungsten. And let's see how the cameras see it differently. Now, I'm sure a lot of you already know what to expect, but let's take a look and see what it goes. So the first shot here is an Alexa with tungsten LED. Tungsten. So tungsten again. LED. Tungsten. LED. So there it is. Day in our life. This is the kind of thing that we're dealing with. And you can really see how, on the one hand, you would expect the tungsten setting to be homogeneous across all platforms. They're not. So the question is, well, why is that? And this presentation is going to make an attempt to try to shed some, bad pun, shed some light on this issue. At least try to bring a better understanding of what's going on. So understanding visible white light spectrum. Traditionally, we've had a way of looking at light, which is through the CIE color space chart. By the way, there's some people in the waiting room.
Yeah, Frida, maybe you can assign me the host again, so I can take care about that.
No my problem. Apologies. Yeah, host. Oh, it won't let me do that.
That's probably because you're sharing your screen.
Oh.
No, we tried it before, but okay.
Were we sharing the screen at the time?
Yeah.
Oh, darn. Okay, I got to go back. Sorry. Technical delay. Let me stop sharing my screen. Sorry about that, guys. Okay, Alexander, you're the host. And
yeah.
Let me go back to share screen, if I can do that.
No, that shouldn't work. Okay, I let the guys in. Now I make you the host again.
Well, you should be able to open it up to just let them in without having to wait.
No.
Okay.
Have you tried making him a co-host?
Maybe that's what it is.
You should be able to let other people share the screen without needing to be a host as well, I thought.
Yeah, pretty sure you can give permission to.
Okay, I'm not seeing it on my screen.
I think on the share screen function, you can select who can share. I think you can select somebody else to do it if you're the host.
That's correct, Bernie. It's a downward click on the share screen, green button, bottom center.
Okay, well, say that again on the.
Whoever is host.
Yeah.
You are the host now, Frida.
Yeah, I'm the host.
Right. What I'm thinking is if Alexander stays as host, but Alexander, you should then be able to allow Frida to share his screen as host without having to make him host.
Okay, so let me just give it back to Alexander.
So if you give him.
Okay, Alexander's the host.
Okay.
So now if you go to the share screen button at the top, at the bottom, you should be able to allocate somebody else. Meantime, there'll be a short intermission, everybody.
Frida, maybe you can try it.
There we go. Got it.
Okay.
Cool.
Thank you, guys. Thank you, guys.
Are there any other questions?
All right. As I was saying, when we think of visible light, we've always looked at it as a CIE color space chromaticity diagram from about 1931. There are other chromaticity diagrams that are a little more modern, but I find this one is just an easy one to wrap your head around. So when you look at the outside perimeter of this horseshoe, that's where all the saturated colors are, all the colors of the rainbow. And this is basically what our eye is capable of perceiving. In the middle of that chart is you can see the white zone where all these colors converge. And through the middle here is a curved line known as the Planckian curve, or the black body curve. And depending on where along that line, the Kelvin temperature will fall along that line. So that's one way of visualizing what our eyes can perceive. Another one is just very simply the Kelvin spectral scale. Our eyes only see from 400 through 700, much like cameras do. To the right of 700, we have IR. To the left of 400, ultraviolet. The black body curve, Planckian locus. Now all white light tracks along this curve, and each one of these intersecting lines is essentially a Kelvin. You can be anywhere on that line and still be referred to as Kelvin. So now, depending on where you are on that line, it may appear somewhat green or magenta. So when we think about tracking along this black body. When we say a black body, what is a black body? Well, it's kind of, you have to imagine sort of like a filament of a tungsten filament. And so as that tungsten filament heats up, that Kelvin tracks along that curve. So as I said, depending on where the color point falls, above, it'll appear somewhat green. Below, it'll look somewhat magenta. So when it comes to, blending color, we had a lot of experience doing that in the fluorescent world. So we've always developed our own lamps, and so the idea was, well, why don't we apply our experience in phosphor development for fluorescent lamps? LEDs are essentially phosphor. Why don't we do the same thing? So we started off with a 2700 Kelvin, and then we did our 6500 Kelvin. And we thought, what could be easier than just blending the two together? And now we have a full Kelvin range. Well, one of the things we noticed right off was that it's a direct linear relationship. And so our very first product that we produced were bicolor. And as long as you're shooting within, the zone closest to where the starting point was, there was never any kind of a color issue. But the minute you started blending the two, you started running into problems. Because obviously, once you're on that linear blend, you're now off the Planckian and you're looking magenta. So that amounted to about anywhere between an 1/8 to a 1/4 correction. And that would lift you back up and put you on the Planckian, and hence got rid of the hue. So now how to do that efficiently, though, without having to add gels? So the idea was, well, why don't we just add some RGBs? So that was the next step in our development. So we went from the bicolor very quickly into a 5-color system where, using RGB LEDs, we're able to actually lift that color point as we tracked across the Planckian and try to keep it on the Planckian. So now we'd also went ahead and said, well, first of all, we have to understand, where do we want to start? Where's our clean point? Now, in the old days with Kodak and Fuji would share their spectral response data with us. They felt it was in their best interest that we understood how their film responded, and we could then tailor our white points to harmonize with the response of the film. When it comes to electronic cinema cameras, none of the manufacturers were willing to share that data. So I reached out to the very same engineer who helped us develop the first fluorescent lamps, and he helped figure out, first of all, by modeling the cinema cameras and determining what their response curves looked like. And of course, in the process of doing that, we discovered that they weren't all alike. So that set up the next dynamic. And we discovered that some cameras tracked above the Planckian, some tracked on the Planckian, some slightly below, some tracked on, then wandered off, then came. It was a bit of a nightmare. So, like every camera, or like every film stock used to be unique, we now have to consider that every cinema camera has also its own unique characteristics. So we would choose a camera, or we would choose a film stock based on its spectral response. There were certain film stocks that had a certain green bias, and certain cinematographers wanted to have that. There were other reasons for going with other film stocks, but it was a cinematographer's decision as to which film stock to work with. A bit of history is always good to understand this, and that is, historically, lighting technology is always harmonized with imaging technology to produce the best images. And if we go back to 1901, the film stocks were 5 ASA, and yet they were shooting in a studio. I mean, my early thoughts were like, Edison's rotating stage, it was all daylight lit, and that's how they achieved a light level you could actually photograph at in 1901. But then I saw these images from those early films, and they were obviously done interior, yet they were soft lit. And what exactly was that? Well, I came across these images of Cooper Hewitt mercury discharge lamps. Now, you have to remember that film stock in those days was orthochromatic, so it was only sensitive to blue and green spectrum. So here was a light source that was actually perfectly harmonized to the response of the film stock. Knowing what we know now in this COVID-19 world, that lamp was more than likely a UVC lamp and was doing nasty things to actors' eyes and their skin. And when I read early accounts of that period, they would be wearing yellow glasses between takes. And there were complaints of eye irritation. It's basically welder's eyes. I mean, this was not a good thing, what was going on over here. And this image from about 1915, around 1918, somewhere around there, this looks like a whole bunch of Kino Flos, but here you have, these were all Cooper Hewitts. And what was unique about them was that in order to ignite them, you had to tilt the lamp. The lamp looked very much like a fluorescent lamp, except the one end of the lamp had a giant ball of mercury. And by tilting the lamp, the mercury would run to the opposing end of the lamp, strike a cathode, and then as you tilt it back, it would draw a plasma stream. So in this image, you can actually see all the pulley systems that were used to tilt the fixtures and ignite them. So this is a image taken from Metro Studios before they became Metro Goldwyn. So again, to me, it was interesting that technically we always had a light source that harmonized beautifully with the recording technology. When we go further into our history, carbon arcs, tungsten quartz, HMI, even the fluorescent was a full spectrum lamp. The fact that it had a mercury spike, we took care of that by making sure that the color point was on the Planckian. So the effective green spike was not, didn't register on film. So now for the first time actually in our imaging history, we're dealing with a light source that is discontinuous and not necessarily perfectly harmonized to the recording technology. And herein lies some of the challenges of what we are dealing with. So how do we measure, how do we figure out, first of all, where do we stand on understanding this light that we're going to be shooting under? So here's sort of the standard array of handheld lighting instruments that we've used historically. Many of you will recognize the old classic Minoltas, the Color Master Gaussen. That was another one that was out there. And you know, they were designed around the response curve of film. And this was one of the reasons that we've had issues in trying to define Kelvin. These were not very accurate meters. These were just very simple tools. I think they were great for comparative data analysis, but as a definitive meter to give you a film correction, I think they fell somewhat short. For those of you who still have these, you know, my recommendation, I say this all the time, is either put it in a museum or gather up your friends, throw a garden party, pop a bottle of champagne, bury these suckers because they really are not doing you any favors. The one instrument that does stand out though as possibly addressing more of the concerns of the cinematographer would be the Sekonic C700-800 series. That one actually gives you data that can guide some of your decision processes. Does it give you definitive corrective data? Not exactly, but it does have a number of useful indexes that will help you at least fashion your opinion about a certain light. So in the fact that none of these meters were giving me the kind of actionable data I needed, I said, well, we're going to have to build our own. Actually, let me just jumped ahead of myself. Just to understand some of these indexes that we do have available. CRI is the one that most of us are very familiar with. Again, this is related to human eye response, also known as photopic response. It can evaluate anywhere between it's basically two standards, 8-chip analysis or a 15-chip analysis. Now the CIE and the IES have already over the last few years rejected CRI, and they said when it comes to LED as a source of evaluation, we should avoid this by all means. yet still manufacturers are using it. And I think part of it is just that the test labs haven't yet fully embraced or are offering the next standard of evaluation, which is being recommended by the IES, and that's TM3018. Now, in principle, it's similar to CRI in that we're comparing color samples, but instead of 8 or 15, we're using 99 color samples. And that's sort of a rendering on the left of what one of our, this was our a SLEB 850 that I took a reading off of. Now, there are a large number of indexes you can measure with this IES TM30. The two that are most relevant to us, one is RF or fidelity index. Now that characterizes the average difference in color for these 99 control chips at a given Kelvin or a reference source. And the other one is Gamut index that characterizes the average saturation level. And on the display there, as I'm showing it right now, you can see the values that it's indicated. The data is scored from 0 to 100, 100 being an exact match. And we're seeing in the gamut on this particular device, we're seeing a value above 100. So since these are all just, it's mathematical, it's possible to be just slightly over, but again, within tolerance of the meter, I think those are very high values. Yet, how do I use this data? If I'm trying to correct another instrument that is next to this, I'm trying to match them up. I can't really, there's no data I can pull off of this that I can readily use to try to match up. So no actionable data. TLCI, I'm sure many of you are familiar with this, the Television Lighting Consistency Index. Now this utilizes average response curves from several modern HD broadcast studio cameras, as well as CCD and CMOS sensors. Excuse me. It does provide a subjective color comparison between a test source and the reference source. And you see that in the Macbeth chart, where you see slight offsets within each color swatch. So as a subjective view, I think it provides data that you can at least evaluate for yourself. Yet there's still a danger of a seemingly high TLC value may still result in certain unacceptable green magenta hue shifts on some cameras. And there's still no actionable data that a cinematographer can use. And again, it's not specific to a cinema camera. These are averaged curves. And when we're working with specific cameras, I think the data set we're working with has to be a little narrower in order for us to be able to use it as a on-set tool. SSI, many of you may have heard of this already. This was developed by the Academy of Motion Picture Arts and Sciences. And this has grown out of the same frustration that I have and everyone else has had about how do you evaluate a lighting spectrum. So it's not based on human vision. The Academy decided, let's just forget about what the human eye sees. Let's forget about the camera sees. Let's just look at the actual spectrum. And how does that differ from either tungsten daylight or another reference source? So over here, that yellow line represents tungsten light. An LED source is overlaid on that reference. And now these areas that fall above or below the reference, those are calculated to an index that would predict whether the artificial source is appropriate or not. And it's, it's given a scale to 100. And these are the words from the SSI directory or directive, and it says high values indicate predictable rendering by most cameras as well as quality of visual appearance. Low values may produce good colors with a particular camera, but not with others. Now, if that's the, and this is where I have my problem with the index. I think this is a good start, but I think we need to be a little more specific. This way of evaluation, I find somewhat too vague. I can't use that data in any sort of actionable sense. So understanding that offset to an LED, of an LED to a natural light, it's of academic interest, but how do I use that? Now, one thing can be said, you can use this index to try to say compare two LED sources and see how they differ. Yet again, there's no actionable data that tells you what you need to do in order to move the two closer together. So the fact that it doesn't relate to the camera, I think is an issue. The fact that there's no actionable data that I can pull from it is the other part that I sort of have issues with. My concern is when you use SSI and you look at all the different indexes, when you talk about the evaluation of a color point that has a high or a low value, what's to determine what is a good high value or a bad high value? And so in this case, we're looking at that same light source that I showed you earlier. And CRI, we don't want to use, but it gives us a high value. So from old school, it's pretty, these are good numbers. TLCI also indicates a high value. SSI is a low number. So in relation to all the other high values, SSI would tell me, well, this may not be something that I necessarily want to work with. When in fact, this light source is actually really well suited to the cinema camera. So I would hate to see this methodology applied in pre-production where you're evaluating fixtures, what am I going to work with? Mind you, you test enough instruments and you may find out that 71 or something in the mid 70s is actually a decent number. So finding conventional measurement devices inadequate, we said, we have to develop our own, and working together with the same engineer that helped develop our early lamps. When I went over to Kodak in Hollywood and asked them about how to develop a better fluorescent lamp, they had this wonderful spectrometer, which had the response curves of film stock. And they also had additional data you could input, which were a broad selection of lenses. So even lens filtration or lens coatings could be applied to the calculation. So we actually were lucky enough to have that same engineer develop our spectrometer. And this is sort of my work field, what it looks like. I'll just give you a quick run through. So for us, it was important to first of all figure out what is the camera actually looking at? What is it capable of seeing? And once we understand that, we can actually apply color points that harmonize to the camera. So down here we have the raw scope. So using a spectrometer, a scientific instrument, that's basically what the raw scope records. Once it is calibrated and essentially cleaned up, that's actually the true rendering of, that's our starting point. It's about a 2700 Kelvin LED warm source. The other thing to look at is, remember the CIE color chart, the XY position on the black body curve, and we can see that it's actually positioned on the curve. So that's a good starting point. We have then 3 rows of camera data. We have the Amira, the Red Mysterium, and the 8K Panavision Red. It's a red chip, a Monstro chip, I believe. And then we broke down the response as a very much like a Macbeth chart, and it gave us values for PRI. Some of the other interesting data fields were what we called, so the correlated color temperature on this particular lamp, which came in on the spectrometer at 2659, so we call it 2700. We then were able, once we had the profiles of the camera in there, we were able to see how the camera actually rendered that light source. So we know that it's 2659. The Amira rendered it at 2718, the Mysterium at 2558, and the Panavision at 2391. So already it's telling us, which we kind of saw in that first demonstration that Jeff had put together, that not all light is seen the same by the different cameras. Now, the fact that this is a somewhat discontinuous spectrum also plays into it, but we really see how already in just a fundamental basis, the cameras do see the same light source differently. The next line under here was photo CCT, and this we did as just a personal reference point for myself. This is based on the old meters, the old Minolta meters, and we saw how those would read that Kelvin temperature. So they always read it warmer, which goes to explain why our KF55 lamps, once people actually acquired handheld spectrometers, they said these KF55s are never 5500 or 5600. They're more like 6500. And that, in fact, was what it's always been. So we decided to call it a KF55 because that's what the Minolta meter was saying. And who are we to argue with all the cinematographers whose meter they were waving in my face going, this is the Kelvin temperature. Fine, I'll go with it. Below that, CIE XY, again, our XY coordinates based on the black body curve down here. So a lot of good data. PRI was the averaging out of the different color responses off the Macbeth chart. It gave me a very quick reference to the general scope of how well was it capturing that spectrum. And so anything in the mid 90s on up, it tells me it's getting pretty much everything. I mean, those are all decent starting points. The one thing that was most important to me though, was how is the camera seeing this relevant to the black body point, to the Planckian curve? Is it seeing above, on, or below? So here's a data field, which we call gels, and then we broke it down into tenths. So over here, a 1.2 would equal 1/8 of a correction. So we're all well below 1.2. So again, this is essentially a neutral white point. And as we go through our measurements, we started to see how this shifted. And so this data field up here was most important for us when it came to analyzing the difference between cameras. To further understand how, what is light, how do we perceive it? I think it's important to look at our eye response. So here's a spectral chart of how our eye sees light. So we have blue, green, and red at 400 nanometers on over to the left, ultraviolet. We can't see ultraviolet and we can't see infrared. So between 700 and 400, that's what we're seeing. Film light, film response. So here's where it starts to diverge from our eye's response. And the first thing we'll notice is that over here, film had sensitivity into the UV. And for that reason, sky filters were important, UV filters. You did not want to unnecessarily overexpose your sky. So that was a reason for having that. We saw that the red response here was shifted over from the red, from our eye response. And the fact that these response curves here are a little different from our eye also accounted for the fact that film, as much as we thought film was the most fabulous recording technology in the world, still had deficiencies in certain wavelengths. And those deficiencies fell right down here into these ranges where we had trouble resolving cyan or teal colors, or in the sort of the 500 nanometer range, yellow oranges. Not quite as noticeable, but there were still issues with that. And for that reason, it was very important as cinematographers to coordinate makeup, art direction, costume, to make sure that these colors would actually render out on film correctly. And there were often enough times where after having shot a film test, one of those departments will go back and make an adjustment to their choice or selection of colors so that the film could render it more appropriately. Here is the typical response curves of an electronic cinema camera. Now, this is a good camera. I'm going to show you a couple of curves. It's not important to say which camera it is. What is important to point out that the cameras are different. And when we're trying to understand differences in response to LED or discontinuous light, this is an element that really plays strongly into it. So here we have a camera that very closely follows eye response. And it's a camera that is in heavy use. Here's another camera. And again, you start to see some immediate differences. A somewhat broader red response, but still at 700, no IR. And that's usually because the IR has been filtered out. But interestingly enough, there is some response in the ultraviolet. So knowing this going into a shoot with a camera of your choice, it's nice to know that you're going to have some sensitivity into the ultraviolet. Here's another camera. Very narrow responses. Great color though. A lot of people love this camera. But again, it just goes to highlight these are differences. Another part of what we need to understand when it comes to understanding how we're rendering colors, to understand gamut. And now Gamut refers to the entire range of colors available on a particular device, such as a cinema camera, a lighting fixture, a projector, or a monitor. So that is your typical Rec 709. And everything that falls within that Rec 709 is the color that can be reproduced. So the saturated colors that our eye perceives that fall out here, 709 is going to reproduce them at a somewhat lower saturation point. Other common gamuts that we're familiar with, P3 for digital projection. You see how it starts to expand outwards. 2020 for Ultra HD or for HDR10 TV displays. And one that I'm going to talk about a little more extensively as we move along is ACES, which covers the entire visible field. Now, a camera may have a wider color gamut than can be displayed or projected. So the fact that we recorded, or the fact that we've modeled or profiled these cameras now gives us also the ability to display the gamuts. And so I thought it would be interesting to actually look and see what the differences were between the gamuts. We saw that there are spectral response differences. How does that play out in a gamut? So in no particular order, so I'm not, it's irrelevant again, which gamut belongs to which camera. But again, what's important here is to see the difference. So 709, and here goes. I'll do it again. So some of the things that stand out, obviously, is one camera has a broad response in this area. Another has a very deep red response. And the other ones all have varying degrees of red response. All of them follow very closely the outside edge. So when we're thinking of Rec 2020 later on as a workflow, these cameras are all capable of rendering colors in that 2020 space. Since we modeled film, yet we never think of film in gamut, I thought, well, now that we're in an electronic world, what would a gamut have looked like on film? So there's your 2020 space. There's tungsten. And there's daylight film. So what I found interesting about this is that most films that have been converted from film to display have all been done primarily in Rec 709. So if we're now going to be remastering in 2020, you can actually see that there is going to be information that was captured in film that was projected that the eye could perceive. Now going to 2020, your viewing experience is going to be much closer to what the viewing experience was like in a cinema. So the 709 was a compromise, but again, that compromise was primarily in the more vibrant colors, the higher saturated colors. Everything that fell in the white zone in here, that would still remain the same, whether it's 2020 or 709. ACES, the Academy Color Encoding System. Now, this was defined by the Academy of Motion Picture Arts and Sciences as a means of creating a standard for holding spectral data, very much in the same way as negative, how we hold spectral data in a film negative. Now, ACES encompasses the entire visible spectrum. So this was designed as a future-proof data collection system. And so they refer to it as a digital source master. So through the use of programming language called color transform language, or CTL, once you've mastered your image in ACES, you're not going to have to remaster it in other color formats by simply taking that color data that you've created as a cinematographer. And now you have to remember, this is also holding all the look that you put into it. All your color timing and everything is now captured in ACES. With a CTL, you should be able to transform it into the next the next display technology without losing any of the integrity of the image. So the ability, the fact that there will be colors that could render more saturated in 2020 than in 709. If it was originally mastered in 709, yet you have the capabilities of now increasing saturation in 2020, the question is, was that the cinematographer's intent? So there's a bit of a cutting edge, a bit of an issue here when it comes to who reaches in and changes it. So as a cinematographer, if you lamented the fact you couldn't get to some of those colors and you remastered in 2020, great. Go ahead and let the cinematographer remaster it. But if you're a cinematographer who was going for muted tones, and after many years, someone else now sees this and goes, yes, but look at the original data had all this other color data. Why don't we just go for broke here? Let's incorporate all these other colors. Is that something that should be allowed? So it's more of a moral discussion, I think, at this point. The objective is to maintain the integrity of the author. So hopefully ACES will provide that. This is an ongoing gamut that is constantly being added to and being modified, but sort of in a nutshell, to make it easier to understand, that's sort of my explanation for it. Kino Flo has a gamut, as do all lighting fixtures. That's what ours looks like. Rec 709. So we can produce everything that's going to be in Rec 709. P3. There's a few saturated colors there, as well as 2020. So some high intense greens, some yellows, but we're going to get most of the reds, maybe just down here, there's going to be some red. So bottom line is there are going to be improvements being made, I think in general, to LED technology that will allow manufacturers such as Kino Flo and others to expand our gamuts. But here's sort of a simple rendering. So the RGB points really define the range of the gamut. The full white spectrum LEDs, they still define the white response of that fixture. And again, that white is common to all of these gamuts, falls in the middle. So as said, the color gamut of a fixture is defined by the primary points. Now, when you combine, say, green and red to make yellow, that's referred to additive color mixing. So you have those three color points you can manipulate and blend to achieve a saturated color. Now, if you're designing a fixture to, say, try to match more accurately to theatrical gels, well, you can see already that the gamut here is somewhat of a limitation to getting to these saturated colors that fall outside the gamut. So, excuse me, the way to broaden that range is to start adding other colored LED elements, such as amber, cyan, lime green, rose red, and potentially others. And so with that, you can see you can actually expand it and start to get into some certain saturated areas that you might otherwise not get to. Now, the one thing that's common to all of this, of course, is the white spectrum. Full spectrum white ensures the best skin tones and the best skin tone reproduction. A full white spectrum will also illuminate and reflect colors back to the camera, and it may even reflect back off saturated colors that fall outside the camera or the display gamut. So there is another way of achieving color points that can't be produced through additive color mixing, yet they can still be done through adding color gels. So as long as you have a good full spectrum white, it has sufficient colored wavelengths in it to display color points that may well fall outside of the gamut or fall outside the range of RGB elements to reproduce. So by applying a gel, now we're referring to this as subtractive color mixing. So the color gel subtracts all the wavelengths that do not pertain to the wavelength of the gel. And in this case, you can actually step outside of the gamut. So it means don't throw away your gels. I think they still serve a purpose. So when we're thinking about this additive and subtractive, there was an interesting situation arose at the American Film Institute. And the AFI fellows are required to come up with a lookbook prior to shooting where they can review how they want this film to look. So it's a combination of images, of all kinds of notes. And one of the exercises they had a production that was where the Roscoe Storaro yellow is going to have a sort of a major color theme throughout the film. And so prior to shooting, they did camera tests and wanted to understand how these LED fixtures they're working with, or the tungsten light, how would all this harmonize? How would this work out? So what I'm going to show you now is a color test that it really goes back into this whole difference between additive and subtractive color response. So the first thing they did was determine that tungsten light measured in around 2900. They set the camera to 2900, and then they applied a gel to it. Now, in this demonstration, I didn't use Storaro yellow. I didn't have it. I had some Leo 101, but in principle, the test held up. So then the next step was, okay, so tungsten, gel on tungsten, that looks good. The camera saw it well, the eye saw it the same way. Let's take a LED fixture, let's dial it to 2900. The camera is still set on 2900. Let's add a gel to it. And yeah, that worked out. Now let's just do an additive color mix on the fixture. The fixture was still set at its white point of 2900, but using the additive feature by blending red and green together, let's come up with the yellow and see what it looks like on camera. And it looked like this. And of course, something obviously was wrong. Where was it? Was it a setting on the camera? No, the camera was still at 2900. It worked well and everything else. Was it the translation of the data from the desk to the LED? No, they took it offline. They tried to adjust it any which way. Never got out of this green rendering. So my hunch was, I bet it had something to do with the response curve of the camera, and how, with a camera set to 2900, how, its ability to resolve additive color mixing between red and green set at 2900. So let's just dial the camera back to 6500. It's native, or D65. It's native color. See what it looks like. And it'll look like that. So this told me that the camera's ability to resolve that narrow band of yellow was not, the camera just couldn't resolve it. So I thought it'd be interesting to now look at how that actually played out spectrally, looking at the graphs, and how do we better understand what the camera is looking at. So with a 2900 tungsten and the gel on it, so the red line here represents the tungsten line, add the gel to it, and it's still capturing a huge volume of spectral data. So that surprised me. I expected that to be somehow narrower. The next one. So again, now here, this blue line, I don't know where are we here. So here we have our tungsten on the gel. Here's our 29 tungsten, but here is this gel on a 2900. And you see already how the shape has now gotten narrower. It's gotten a little, not as much spectral data. And you can see a slight difference between the tungsten on, the gel on 2900 LED versus tungsten. But still, camera saw it well. You could run with that. This next one is the one that really indicated why there's some huge differences. So the additive color resulted in this very narrow rendering of yellow. And so all that other spectral data that that the camera would normally see has now been condensed. So huge difference between subtractive and additive color. And we found this later on in other issues where once the electronic cinema camera was dialed down into a warm zone, it was far more, there were far larger differences in rendering between these different cameras. So again, this is, points to a reason why it's very important to do the testing up front before production, so you don't run into an issue like this. And there's no way you can correct this. I mean, this is just a symptom of this kind of color mixing. There was one other color gamut I think is sort of interest bears mentioning, and that was a Pointer's gamut that was defined by Michael Pointer. He was a Kodak engineer, and it's based on the approximate range of matte surface colors that he referred to as real world colors that a display device can reproduce, and it comes up with this rather odd looking shape. And so these are colors, if illuminated by daylight, for example, that would be reproduced as a matte surface reflection. And you can see that it all pretty much falls within just, 709 will cover most of that. And 2020 encompasses the entire real world colors. Again, not something that we'd necessarily concern ourselves with. I just thought it was interesting. When we talk about white light systems, there's so many different ways of producing white light, and it bears going through them because this is what we're dealing with when we're on the set. This is sort of a rendering of all these different ways of looking at white light. So this first one up here is bicolor, standard bicolor. We know what the issue there was. When you blend them, you have an issue. Simple RGBs, red, green, blue. Theoretically, yes, you can hit white, but it's such a narrow band white, it doesn't give good rendering. Single white RGB, very common in our industry. Issue there is when you move off your white point, the only way you can do it is through narrow bands of blue and green. And so the ability to capture a broader spectrum of white light at that point is diminished. Red, green, blue, amber, I think doesn't do much to enhance the white ability. It does help when you're trying to render out certain gel colors. The one that Kino Flo works with is 2 full spectrum whites, and the theory being here, with 2 full spectrum whites, at least we have the volume of white spectrum that's essential for skin tone rendering in the daylight versus skin tone in the warm as well. We've got them both covered. And then using the RGBs to track the Planckian. As an aside, whatever you can get out of it for color gels, it is what it is. Is it going to be as broad as, again, I pointed out the earlier issue with just doing RGB color blending for gels. It does have some limitations. The other two are, again, the other theory is, well, we'll work with red, green, blue, but we're going to add a lot of other additional wavelengths to try to flesh out the spectrum. Those work as well. The issue there becomes more or less, how do the different cameras with the different response curves, how do they render those? And it all just starts to get a little more complicated, and it also gets to be a lot more expensive to develop that kind of a product. And there are other ways of achieving a wide spectrum. So again, this is what we're dealing with though on a daily basis on the set. So just simply grabbing a fixture, you need to be aware of what its color generation is, or its white light generation is, so as not to be disappointed later on when they don't necessarily align. So white light, it's not all the same. So this is where the analysis got to be interesting. By the way, should I pause for a moment to have any questions before I get into all the graphs?
Frida, there was a question that went up a little while ago about where is it? Gwillan, have I pronounced your name right? Do you want to unmute and ask the question yourself? It says, I think the differences between camera responses are valid. I also think that new lights have to pair with all the differences in camera responses. What do you think about this? What way are you choosing? I'm guessing that's something you might be getting onto, but is it something you want to address at the moment?
Yeah, no, I'll be getting into that. Yeah. I mean, we ended up deciding on a couple of cameras that were the most dominant cameras right now in the cinema field. And we're going to be redoing a lot of that data gathering this year to bring it up to current standard. So again, this is a research tool, and this is sort of the research that guided our decision processes, and why do we choose to do one thing over another. So in this case, go ahead.
Yeah, I was just going to say there's also another question which I think also you'll be getting into, but do LED manufacturers actually have the ability to produce an LED fixture that can have any required peak center point? Are there peak colors not currently possible to be generated?
Well, again, between all the different manufacturers of lighting instruments, there are varying levels of competency in understanding what the goal is, number one, and how to achieve that goal. So that being said, it really comes down to a manufacturer and how much they understand of what the ultimate goal is. We chose to make skin tones number one. Coming out of Hollywood, if that star doesn't look good, that's your last gig. So the whole key to being a successful cinematographer in Hollywood is to make sure that the high-priced talent looks fabulous. And so that was sort of the guiding principle over here. Yet at the same time, it also has to render all the other colors accurately. So.
And also, just on that, the Ali Hunter asked what you use as a standard for skin tone rendering. Is it always white Caucasian skin tones, or do you routinely test for other skin tones?
We've looked at different skin tones, and again, it comes down to these reflective issues. And this is where having a full spectrum white gave us the most consistency. Having a single white, and this is what I'm going to illustrate now, there are spectral deficiencies in a single white, and they do show in subtleties. And as we go deeper into it, you're going to start to see some of those differences as well in some of the tests that I show. In this particular graph, what I wanted to illustrate is a difference between again, these are all discontinuous light sources, we have to say. This is not tungsten. This is a rendering of tungsten, a close approximation. So with the two whites, we have all this volume of spectral data defined by the green line. The single white is defined, excuse me, by the red. So this is 3200. When we take this into our analysis, we can see that actually the XY coordinates match up nicely. We see that the PRI, the photographic rendering index, is actually pretty good. We see a difference here of 96 and 93 between the Amira and the Mysterium. So right now I'm just comparing the Amira to a double white and a single white. So we just get an idea of what that difference is. And then we just compare it to another camera. In this case, it was a Mysterium with a single white. We see over here already in the way the camera sees it. So the full spectrum, the two whites we see as 33. 32 is the actual Kelvin reading that is blended. So 3372 is about as accurate as you're going to get. The Amira on a single white, and again, I think partially because of the diminished spectrum, is seeing it actually a little warmer than 32. And the red Mysterium here sees it as 2859. So, a off from 32. Both cameras are off from 32, and because they're both working with a single white. When we go to the color correction, the full spectrum of the two whites need no correction, a 1/8 of a correction on the single white on the Amira, and almost a 1/4 correction on the Mysterium. So again, the same light source, comparison between two cameras, you start to see the difference. Anyway, it is what it is there. So now when we go to daylight, again, we see the spectral quality differences. We try to avoid these deep troughs because that means there's less response to colors in that range. So we try to keep the curve as smooth as possible. This peak here is your exciter line. That is the 450 nanometer blue pump that all LEDs have. Some LEDs have a slightly different pump. It could be 430, it could be 420. Those are newer LEDs, and I think our industry will be moving in that direction. When it comes to looking at how that looks on the analysis, XY coordinates were a little different. Now in the daylight range, we can accept some of that difference. It doesn't appear as dramatically different to our eyes. PRI, again, those are all numbers that we can work with. On the gel correction, this is where we're also pretty close in this particular case. So daylight, again, daylight is one of those more forgiving camera positions where we can accept those colors. A slight 1/8 of a correction on the Amira and the Mysterium on a single white. When we're looking down here at the camera response, we can see that the two whites are rendering a little cooler than the actual CCT, and on the other two, a little warmer than the actual CCT. So another way of looking at white light is saying, okay, we're not going to use any white at all. We're just going to bank in a whole bunch of different wavelengths. And let's see how we can construct a wavelength out of multi-bands. And this is a rendering at 3200. So the red line is the multicolor. The green line is the two whites. And we can see again the difference in volume of spectrum that is recorded or is being generated. And again, if you're not generating, the camera can't see it. XY coordinates were close enough, I guess. It is what it is. PRIs, can live with that as well. Those are all good numbers in the 90s. When we look at the color correction necessary, actually the only one that had an issue here was the Amira on the multiband needed a 1/4 magenta. The multiband on the Mysterium was as zeroed out as the two full spectrum whites. So here the only difference is it's not going to have quite the volume of spectrum that it can record, yet a 94 number is still going to be pretty good. So in general, you most probably won't even notice a huge difference in color rendering. You might notice it on certain skin tones, but it actually showed up pretty well. Now, keep in mind, this here is a 0.07, no correction necessary, neutral white at 3200. The next one we're going to look at is that same construction of spectrum through multibands, but now going into 6500. And again, we're seeing the multiband has got various spikes, and we'll see what that results in. So in this case, we have XY coordinates match up nicely. The PRI numbers are all acceptable. And up here is where we start to see where things go haywire now. Sorry, it's jumping on me. The Amira needs as much as a 1/4 and an 1/8 correction. And the red Mysterium now suddenly jumped to the same kind of correction, a 1/4 and an 1/8 correction. So where you were comfortable with the Mysterium at 3200, and you said, well, I'm fine there, this will render out fine in daylight. Suddenly it went green, and we have to apply a magenta correction. So this only becomes an issue when you're mixing lights on a set. And if you don't catch that as a 3/4 backlight, let's say, and suddenly it's gone very green, that might create real problems in color timing down the road. So just assuming that one light works in 1 Kelvin setting, it's going to hold its green magenta balance as we go higher up the Kelvin scale, may not necessarily hold true. Now, that's not to say that that particular fixture could have a new algorithm written into it that might accommodate that. But again, I'm just taking instruments that are readily available in the market, just as you would, and finding that these are the kinds of anomalies that jump out at you. Here's the dog's breakfast that we face on a day with multiple instruments on a set. We have the 2 full spectrum lights, the single white and the multiband. And you can just see how varied all those spectral curves look. And so from that, we expect some consistency. We notice the XYs are slightly off, which is actually, when we look at the camera CCTs, there are some big differences there. We look at that and you can see right here, the camera CCT, we're going from one camera seeing it as 7,500 to 47 to 55. And each one of, so just to be sure, so we're looking at it. So there are 3 different light sources, the same camera looking at all 3 different light sources. They're all dialed into 6,500, yet they're coming across differently as a true Kelvin, and then the camera is also seeing it differently. So now you've really compounded the issue where you think your instrument is all dialed into 65, yet what's actually coming off of it is far from it. PRI, close enough. And slight correction, heavy correction. If this was on a set where this particular light source over here was being used as a 3/4 back and someone with light hair is walking through that light, and now suddenly for no motivation whatsoever, that hair starts going green, and you're sitting in the color timing suite going, what the hell happened over there? How do we correct it? So now you're into doing some very fine finesse work, which if you knew it on the date, you would have avoided that, or you would have undertaken some corrective measures to try to knock that down. So again, it's just an illustration of the kind of pitfalls that can fall on us. So matching white light. So how can we harmonize fixtures when they use different color mixing approaches? Well, as I just showed you, you can't. You can get close, but is it close enough? And the only way to determine that is through doing some testing. Without doing the camera tests, you're going to be hard pressed, and you don't want to be figuring this out on the day of the shoot. You can use XY color coordinates. They can match Kelvin, but the difference in spectral distribution, as illustrated in the diagrams again, they make that color matching challenging, especially depending on the camera you use. So the camera response curves now play into it. And so that could be either greater or less discernible. So when it comes to trying to match color gels, the color space such as Rec 709, P3, 2020, these all define the chromosticity of the red, green, and blue color points, as well as the defined white. So the white is that D65, it's in the middle, and it's either 100 points to the green, the red, and the blue, or if we're working in DMX terms, those get broken down into 255 increments. So if we're trying to dream up a gel, how do we match a gel? Well, there are these apps such as Show Tool Swatch, and they give you data that you can either have in increments of 100 or the 255 increments. And you can adjust that just by tapping on this little symbol over here. So remember, we talked about Gamut. So this is where Gamut really plays into it, and this becomes very important. We determined that this app actually displays these numbers in 709. Now, a true gel on tungsten falls outside of 709. So when you're trying to match gels using an app, It really comes back down to your fixture and understanding the gamut of the fixture. It also comes into play of understanding your workflow gamut, because even if you have a fixture that is capable of defining a color outside 709, you're still only going to be rendering it in 709. So this sets up a dynamic of unattainable expectations. If you have a director who falls in love with a certain saturated color, and as a cinematographer, your camera is capable of capturing it, yet in 709 is not capable of rendering it, you want to know that before you make the decision to go with that gel. So wherever that color point falls that is outside of the gamut, this app will show you that crossover point. So it'll be on the right color angle, but it'll be at a slightly desaturated color point. Another one of the apps is the LED gel app. And now that defines its color points in terms of XY. Now you can either dial it in for source C, which is daylight, or tungsten. And the XY coordinates will be replicated in either, depending on the one that you choose. And these are independent of gamut. So this is actually kind of good. This is a more accurate way of defining a color point. And the data points may offer, however, they fall outside of the fixture's gamut. And again, we're back into this dilemma of understanding the gamut of your fixture. Now, in our case, you can select the gamut, your output gamut. You can select 709, 2020, P3, and I'll get into that a little deeper. Now, these apps are all available on the App Store. And again, they're useful tools. There's one, I have to mention this, but it's going to be dropped from our software. There was another gamut developed by ESTA. This was a few years ago. It's still on our earlier software, although our latest software has dropped it. And again, out of the same frustration of trying to define colors, ESTA is suggesting using the old Kodak Pro photo color space. But instead of using D65 as Kodak did, they had suggested using D30 or T32, which created some issues, which I can show you later on. So right now the call is let's more likely just stick with XY. So I think XY is going to be the way that the industry is more likely going to gravitate to. So this rendering down here in our menu, you'll see it as ESTA E1-54, but that's going to disappear from our software in the next iteration. So now XY is also a great way to measure reflected light. So say you're on a location, you've got a window, beam of light comes through, you've got nice hardwood floor, and the light that's reflecting off that floor is this beautiful warm tone. Now, how do you replicate that light? Well, the first thing you'd think is you pull out the color meter. What's the Kelvin of that meter, of that light bounce? It's one way of doing it. What it doesn't do, simply a Kelvin reading, does not take into account some of the other tonalities that may be in that floor, whereas an XY may do that. So doing an XY reading off a bounce source, or if you're trying to match some other, let's say a light source on the set, the XY approach may be much better because it'll encompass any other nuances of the spectrum that will maybe pull it off the Planckian somewhat. So my recommendation is use that feature on the XY feature for color matching on a set. So what we've done on our products now, we've incorporated some of these ideas. So XY color matching for replicating Kelvin or reflected colors or gel colors. It's something you can dial in. It takes it outside of our, well, it still operates within the Kino Flo gamut. If you do a gamut selection, it won't necessarily, it won't hold those colors within those gamuts. It's still going to take the Kino Flo gamut. RGB color gamut selection, again, in trying to match color points amongst different manufacturers. The thought here is if we all as manufacturers start putting in a defined gamut, from a board operator's perspective, if you can set all of your lights to 709, let's say, knowing full well that maybe the production is going to be doing its workflow in 709, the likelihood of trying to align color points between different fixtures is a better bet. So the more of us manufacturers that offer this, it remains to be seen how successful we're going to be in that regard. So just as an example of how this works out, I've got a little demo here to sort of explain this. So this is our Freestyle 4. We've set it to a mauve gel. Now this number next to it is essentially just a placeholder number. We have 255 increments that we could assign a gel to. So this gel is assigned at 216. So a board operator on a board, if he selects 216, will come up with this mauve color. This mauve color is as close as we can get to a gel set at 3200. You know, a gel on a tungsten at 3200. And this is within the Kino Flo gamut. So it's defined within the Kino Flo gamut. So if I simply move this now into an RGB space and set the gamut to 709, which is smaller than the Kino Flo gamut, you see an immediate color difference. I'll do that again. So you can see what happens when we take a large gamut and compress those same values into the 709. If we then take it to P3 and ESTA, which had the other color point, oops, go back. Hold on. Just run that again. Over here, I'm going to show you what happens when we input now the values from a 709 value into this fixture. So we now want to take this instrument and bring it into a color space that is 709. So we'll select 709. Now it'll, oops, sorry. I haven't figured out a better way of trying to stop this thing when it's supposed to, so my apologies. So one of the things to notice is once you're in the 709 field, it actually displays Rec 709, and now we can go in and adjust the actual RGB values. So what this has done now, it's taken a much more saturated mauve, but now brought it down into the Rec 709. So you can see it's not quite as saturated as it was earlier. But at least now the camera is going to be able to render this accurately, or the workflow will render it accurately. Oop, damn. Now, once we're in 709, if I go back into my color menu, I can actually jump out of that 709 setting again. And you see the difference between the 709 setting and then the Kino Flo setting. The other thing we decided to do is we noticed that the cameras were responding, that there were larger response differences in the warm tone settings on the camera than in the daylight settings. So we thought, why don't we try to harmonize fixture performance to the response of specific cameras? So the four dominant cameras that we found on a lot of the sets was the Arri Alexa, the Sony Venice, the Panasonic the Panavision DXL, and the Panasonic Vericam. And so here's an illustration of how that would be set up. And you can actually start to see some of the differences in the color response. So with the tungsten being a little warmer than 32, we set it a little warmer. And then we go to the camera lookup table, which is not so much a look as a profile. So the Sony Venice, Panavision, and you start to see these hue shifts. It should be said that the Kino Flo default and the Arri Alexa are very close because we didn't have the camera profiles in there earlier, and we decided, well, we need to pick some sort of a profile because we know there are differences in these cameras. So let's take the more dominant camera in the field, at least from what we were able to determine here in the Los Angeles market, and that was the Alexa. At the same time, we also knew that the Alexa had a very good, in general, a very broad response, and we could tweak that a little bit to favor the Sony and the Red a little more. So we fudged those numbers a little bit just to try to encompass the other cameras and not make them as far apart. But now, once we are able to define the actual profile of each camera, it allowed us to now be a little more appropriate to each setting. So you don't see a huge difference between the Kino Flo and the Alexa, but you start to see it on the other cameras. And again, this on a skin tone is where you're really going to see the differences. So in summary, we have to think of our fixture as a white light generator and a color generator, and that not all white light or colors are going to be the same. We need to understand gamut and gamut selection, know when to use it when dealing with additive color mixing. We should also be aware of your workflow gamut and be aware of unattainable expectations when colors fall outside of that workflow gamut. XY matching, I think, is going to be a really useful tool in trying to harmonize a lighting fixture to a given light or another light source that's on the set or other lighting phenomenon on location. XY for color picking is going to be limited by the gamut of the fixture. So again, this is where manufacturers have to be open a little bit about what their fixture actually can do. What are those color points that are going to be outside the gamut that you're trying to render? And if so, they're going to be slightly at a lower saturation level. Always keep in mind, subtractive color is always an option. If you have a good full spectrum white light, you can always use those color gels. Don't throw them away. And they may get you to color points that simple additive color mixing will never get to. One of the things that I didn't talk about, but it does play into this whole notion of different cameras respond, cameras respond differently, fixtures respond differently. Because we now have the profiles in the cameras, John Schwartzman, ASC, chose to implement that in a real world situation where he wanted to minimize the amount of differences he was going to have on skin tones. He was doing an Emma Thompson movie at Pinewood and decided that he was shooting on the Panavision DXL and said, okay, all the light that's falling on the faces are going to be the freestyle, the Kinos all dialed to the DXL. I'm going to create a zone around the actors that is all homogeneous light that he has control over. And then he'll use the other lighting instruments, which of course, there were lots of other lighting instruments that the rental company had and was insisting that he use. And he said, okay, I'll use that on the studio backings. I'll use it through windows, through shears. So essentially you're setting up two different zones where you can actually justify a slight color tone difference and it'd be totally acceptable. That worked. The colorist noticed immediately. The lighting team noticed, looking at rushes and whatnot, looking at dailies, that there was a color consistency that they hadn't seen before. Producers and the director also took notice. So this ended up, as John was concerned, he said this was a huge game changer. The other thing to think about is when we're picking our choices of fixtures, let's pick an appropriate fixture size for the task. The mere fact that you can dim fixtures down to low levels does not mean that you should take a fixture that can be very bright and operate in very low light levels with it. Because we're dealing with different color points, at a certain point in dimming down, you're going to compromise that spectral distribution that is achieved through these different lights, different colored elements. So it's something that has to be determined in pre-production, and keep in mind to diversify your selection of instruments to have different sizes, especially with so many of us shooting at 800 ISO. We don't need a lot of light now, especially with the broad contrast response of these cameras. It's very difficult to get deep blacks. There's always detail in the blacks where you're trying to maybe get to a more solid, solid richness there. Other note to keep in mind, camera profiles, I think they're best applied in working in the warm light environment. They have very little effect on color gels because that's more saturated colors, so you're not going to see huge impact on their ability to resolve those differences. So very much the way Rembrandt and Vermeer chose their pigments carefully, I think today's cinematographers really have to think about our choice of lighting instruments and cameras as spectral palettes. A good broad spectrum of white light goes a long way in solving color rendering. It's very important for us in pre-production testing the camera and the lighting. This is more important now than ever before. Test your choice of lights as well as how they harmonize with other manufacturers of lights. Test your choice of lights to your camera, not just in daylight, but also in tungsten. You may see that there are going to be some surprises and differences. Today's color science is the 21st century pigment. The fixtures are the brushes. Choose your pigment wisely or suffer those consequences when you're color grading. That, my friends, is it. Everyone still awake? Hello! Thank you.
Oh, that was excellent.
Tremendous.
Yeah, really good.
Thanks.
What a beautifully researched and interesting presentation. Absolutely packed full of information, goodness. For me, it felt like I've just read a really good book that I now want to read again to pick up all the bits that I missed out on. But I'm pleased to say that the aim is that this will be available for everybody to see in the future. Yeah, I'm sure I won't be the only one wanting to have a look through that.
There's a lot of data there. And when I did this, I did a talk where I actually toured with this talk. In Spain, I had cinematographers that I saw at 3 different presentations because they came back to reabsorb what was there. But when you think of it, when we think back of our film days, here you had cameras, didn't matter what camera you had, and Kodak took all the color science and embedded it in the emulsion. All you had to do now is get the chemistry right. And for the most part, you had consistency from choice of camera and film stock. And then the only thing is, tungsten light was pretty consistent. HMIs, we knew it had its issues, and so you could sort of deal with that. But today we're dealing with, embedded color science in a lighting fixture and embedded color science in cameras. And there are multiple cameras to work with. So you're setting yourself up for a very complex dynamic, and to try and weave your way through those complexities, it can be absolutely maddening. And so at least here I've just tried to give somewhat insight, so to try to focus where some of these challenges lie. And as an end user trying to make a decision, it helps potentially focus an area of further investigation to allow for a better choice of tools to work with. And once you have those tools, you're more than likely to go back to them and make them just like a painter. You know, you can identify a Vermeer and a Rembrandt just by analyzing the pigment.
Yeah, very interesting. Alexander, were you going to bring up some of the questions that have come up?
Yeah, so there were a couple of questions during the presentation, and I would just say let's open up the Q&A round. So I collected a couple of questions, so let's see. The first one that I have is from Eric, and he was asking, how do we measure what the camera is reproducing? So I think he wants to know how do we measure the camera responses? Well,
a simple test would be to go ahead and set up a tungsten light on a 18% gray, see what that looks like. And then again, we're using a lot of data analysis to come up with our results. So you shoot that same test versus a tungsten and see subjectively what that difference is. Does it look appreciably warmer? We're doing heavy duty analysis. It's not something that you can easily do on the set. So that's where it's important to do pre-production testing to be comfortable with the settings that you use. If you have a camera that you want to harmonize with tungsten, and you know that your tungsten light may be reading warmer than the camera will see that tungsten light warmer, then you may want to say, okay, we're not going to go with the standard 3200 setting. We're going to increase the Kelvin on that particular instrument. And hopefully you have the ability in the software to do that.
So Eric just sent me a direct message. I don't know, Eric, do you have a mic? So you maybe can just ask your question directly.
If you unmute, you can talk.
Is he here? Oh, no, he says, sorry, no audio. Okay. Okay. So what he was writing was, but showing the camera through a monitor, the monitor will affect the measurement.
Well, you need to have a calibrated monitor to begin with. But again, you're looking at it now subjectively. So you're looking at a shot that's done tungsten-wise, and then you're looking at a shot done with your LED. And just like that test that Jeff put forth, you see those differences. So if you want to go by your monitor, then that's what you go by. And if you want to balance it to eye, make the adjustments on the instrument, on the fixture, to the point where you're happy that it's a close approximation of the tungsten that you're trying to match to, or for that matter, for any other light you're trying to match to. So if you have two LEDs and you're trying to match them, the 18% gray card is a nice way of, once you see it as neutral gray on your monitor without a lot of other hues, and now you go add on to, compare it to the next light source you're trying to match, you'll start to see those differences. And so then it's a little back and forth, but that's sort of the easy way of doing it.
Okay, then there's another question from Nathan Jones. Will you be expanding the camera LUT profile range to add more cameras?
We'd like to do that. I'd like to get a little more cooperation. We had great cooperation with Panavision. They're using a Monstro. I have not been able to compare it now to the red cameras yet. This is something that we're going to try and do this year. We're going to try and update a lot of the camera data that we have internally. And then I'd like to try to bring in Canon. Canon has already expressed interest in working with us to provide us with their cameras to do the profiling. It's just a tremendous amount of work. It takes an awful lot of data crunching to come up with a final, profile. But it's something that we are looking to do this year. So hopefully by mid-year, we'll have a whole new data set to work with.
Okay, so while I'm reading those questions, a couple of more questions dropping in. So just feel free to open up your mic and ask those questions directly. Just imagine we are in a bar and Frida's next to you. So just ask him whatever you want to. But before we do that, maybe Paul Middleton also sent a couple of questions. Is Paul here? Yeah. Paul, maybe you can ask those questions directly.
Okay. Can everybody hear me?
Yeah.
Got it.
There's two questions really that are in some ways interrelated. The first question was over whether manufacturers of cameras, knowing more about their camera responses, that then decide to manufacture LED lights, have any benefits over anybody else, or basically does Kino being able to be tuning their response have a better response than what the manufacturers that may be tuning their fixtures to match their cameras at the moment?
Well, from our research, they didn't do a good tuning job.
Right.
Again, part of that is the illustration I was making. It's a choice of platform that you choose to work in. There's a definite handicap when you're working with a diminished full spectrum white and you're counting on the RGB values to make up the full extent of the Kelvin range. And so as we saw the difference in camera responses between manufacturers, this then becomes compounded depending on what the other cameras are going to be. So since we're not tied to any particular camera company, and our focus has always been try to get as much spectral data to reflect back to the recording source, be it film, be it electronic cinema camera. How do we best achieve that? And so we found with two full spectrum whites, that gave us an economical way of achieving that goal.
The second question that I posed was regarding reproduction of entertainment colors as opposed to trying to achieve sort of perfect white responses. I know it's a question I asked you at IBC last year. The issue for lots of people that are doing entertainment effects is that when you're shooting in tungsten, all of the blues and purples and pinks that you see lovely in real life on camera all just come out as blue, blue, and blue. Is that ultimately an issue with cameras, or is there anything that LEDs can be done so that you don't have to end up shooting at sort of 4400 or higher in order to get those colors to be reproduced on camera?
Well, that's where the test that I showed was so telling. We're always used to, historically, subtractive color production, where you're actually applying a gel to a light source and you see what volume of spectrum was there that our eyes could see and that the camera could see. Once you start doing that additively, it really comes down to how are you generating that perceived color, and is that spectrum broad or is it narrower? And as long as as far as the eyes can see, when that test was done where it looked green on camera, the eye saw it as yellow. It was perfectly fine for the eye, yet the camera just could not resolve the issue. And this comes into using theatrical lighting instruments that are designed for eye response, not for camera response. And so I think this is where a lot of work is now going into, is looking at generating colors through multibands to try to broaden that response in that color range so that potentially the camera can see it better. So you have to decide, can you get an instrument to do justice to all the things that you need to do? Our primary market is the cinema market, where the skin tone is really critical. The colors are secondary. If you're reproducing a theatrical show on a stage and you're recording it now with broadcast cameras, those colors now really become a challenge for the broadcast cameras if they're done through a standard RGB color generation system. So you may need instruments that have more of those colored elements to try to flesh out the spectrum. And yet at the same time, how is that instrument going to render your whites, your skin tones through the entire range, no matter, is the camera set in daylight, is it set in tungsten? So it's a really, you're asking for a lot of heavy lifting out of one instrument. It's possible, yet there is a cost associated with it, and everyone is cost sensitive or price sensitive. So yeah, it's that's where you need to test it in advance and choose the right instrument to render the colors.
So I suppose the final wind-up point of that is it ultimately a sort of law of physics issue that with the way that cameras are adjusted internally in order to cope with tungsten and daylight mean that they simply cannot cope with the LEDs, or is it a lack of control of the LEDs that's missing at the moment?
It's the spectrum. It's the spectrum of the LED. Is it narrow? Is it broad? When you compare the narrowband spectrum of an additive green and red to get yellow, you see how narrow that spectrum was compared to the subtractive equivalent on a light source. That's the difference right there. Then added to that, the ability of the camera to resolve a narrow band color in a lower Kelvin environment. That's the other limitation. Our eyes can adjust for it. The camera just can't resolve it.
Okay, well, Bernie may have some points to add on to that, but from his experiences.
Wayne has a question. Go ahead, unmute, just unmute, there you go. We can't hear you, Wayne.
Wayne, we can't hear you. We can see you've unmuted, but you can't hear you.
No, you're not coming through.
Can you hear me now?
Yeah, yes. Here we go.
My microphone settings on my computer. Hello, everybody. Yeah, one thing that always bugs me, I'm a gaffer, so I'm not really a cinematographer, but I spend a lot of time stood next to cameras. Narrow spectrum, really. Obviously for the close-ups, we always try and use the broadest spectrum possible, and what better than the tungsten light bulb. So, you look at these curves and they're horrifying, really, when you look at them. You look at a lovely tungsten curve or a lovely daylight curve, and you think, great, put a reading of some kind of LED next to it, and you think, Jesus, what's going on, My question is that, we've got RGB, we've got warm white, cool white, we're adding in lime, we're adding in amber LEDs. Is it possible to use phosphors to actually blend these colors sort of, so we get even smoother spectrums? I mean, I always think of it like, I always relate these things back to sound, really. I used to do a bit of work with sound. If you've got a parametric EQ and you're sweeping through those frequencies, I'd imagine, if those frequencies aren't there, you're just not going to hear anything as you're sweeping through those frequencies. Same with light. You're not going to see those colors as you're sweeping through, trying to find those colors. So it's a question of broadening out those, those narrow bands. And with the phosphors,
Exactly.
you guys have got the history of phosphors. Is it not possible to spread the frequencies more with phosphors?
So you can. We did it in the fluorescent world.
Yeah.
In fact, the fluorescent spectrum is a full spectrum. It's broad spectrum.
Yeah, sure.
Our KF55 lamp is still being used in museums as the ultimate source. It's being used for camera calibrations and everything else. What we have here is a technical limitation. This is a limitation of LED technology. And so you'd think on the one hand, there's technology now where we can use as in fluorescent, which was a UV exciter, you can do this with LED. The only problem with the LED and UV pump is the fact that the longevity, the actual lifespan of that phosphor, the stability of the phosphor is heavily compromised. It's a cost factor of 3 times what a normal LED will cost. Then the stability of that phosphor exposed to the ultraviolet is very unstable. So you've got maybe a stability of 2,000 hours. at best. And from what we understand, it immediately starts shifting from the point at which it's manufactured. It's a slow curve at fast, and then it very rapidly drops off. So a lot of research is going into it. At some point, they may be able to resolve that. Some of it has to do with the actual coatings that go on the phosphor itself. There appears to be some ozone reaction that is penetrating through these coatings into the phosphor. It's something that we're tracking closely and following, but we can't afford to bring something to market which within a year or two is going to be so off color, it'll upset you. So what we're looking at now, or the industry is looking at, is trying to migrate that blue pump further to the edge of 400. And what we're seeing too is that some cameras are not responding. When we look at some of those curves, some of them are not responding at 420 anyway. So where film normally ran into ultraviolet, the cameras are able to now actually tailor themselves closer to the response of the LED. So if you look at one of those early curves, it actually comes pretty close to following the response of LED, which may be part of the answer. You keep it within the ability of what the camera can see anyway, and not worry about what our eye can see. So, our ability to see tones from 420 nanometers to 400, that's a subtlety, which I haven't yet found how to actually equate that to a subjective evaluation of what are we losing in that range. But so going back to your question about phosphor, yes, this is the reason that we're working with 2 full spectrum white phosphors, and we've maxed that out to capture as much volume as possible, which is why also once you put a gel on it, there's so much spectral information there that you can get to that color point outside of the gamut of the instrument and still render that yellow.
Okay, yeah, thanks.
Okay, I got 2 more questions here from, one is from Dana. Dana, would you like to ask it by yourself or no? You want me to read it? Okay. Just a second, let me try to find it. Where is it? If I shoot in log raw, how relevant is all this since you can adjust the white balance later?
All this comes into play because you're mixing light sources on a set. So yes, you can. If you're under one light source in general, then none of this is an issue because you can time it all out. The issue arrives on that dog's breakfast of spectrums that I showed, where you're mixing different manufacturers. You have an expectation that you're shooting in tungsten. Now you're adding all these other LED instruments. You expect them all to harmonize. And now you have a 3/4 backlight and you're going, why does that look so green? Or why does it look so magenta? Or why does it look whatever it is that's different? Because your eye doesn't see it, and you may not even notice it during the shoot. And especially if, depending on what your display lookup is on your monitor, there may be subtleties that you don't catch. So this becomes more of an issue of how do you pick the right tools to work with so you don't set yourself up for a challenge later on down the line.
Sounds like you'd want to balance everything to 6500. Is that more?
Well, what you want to do, it's not necessarily that. You can choose to balance all the tungsten, or you can choose to balance to 65. It depends on the scene and what you have in the image. But once you've determined where you want to be, now you want to make sure that the instruments that you choose are going to render and reflect back the colors that you expect to be seeing. And so if you choose different instruments that have different gamuts and have different ways of achieving white light, that means the amount of white light that it's projecting may be different from another white light. So what reflects back off your, let's say, diminished light source is not going to match what your stronger, broader spectrum white source is going to render back. And that's where you start to see some of these mismatches and you go, why does that teal color not look as teal or changes color as he walks through the scene? Yet you think you're all within the same tungsten environment. Or tungsten. So
let's just say, I mean, it sounds like, from what I understood, if I shoot at 6500K, or if I set my, LUT to that, there's going to be better response from the sensor versus if I do that in tungstens. I mean, is that
in very broad strokes? Yes, in very broad strokes, I think you can make that claim.
Yeah.
And the way the cameras respond to discontinuous spectrum in daylight is, I think, more forgiving than in a warm tone.
Okay, so at that point, if I do that and then in post I change it to 3200, did I make any difference doing it later versus on set?
No, as long as you're all within an environment, from there you can just change your Kelvin temperature. I would think it shouldn't. At that point, the image is fixed, and now you're just trying to shift the overall tonality of it. I think that would work. That should work well. The other thing that came up recently in one of our, I think it was in one of the CML chats, was if you applied a color correction gel to the camera and brought it down to 32. Now, I haven't done the test, but I talked to my colorists, and we're saying, they said, well, we all agreed there was going to be a difference. It'll be different putting it on the lens than dialing the camera down to a warmer Kelvin response. And it's something that I'd like to do a test on to see exactly how that renders out differently.
I guess another kind of offshoot of that question is all of this as relevant to using, if I was using one source versus multiple different kinds of manufacturer sources? Is it kind of all more relevant when I mix and match, which is obviously usually the case?
Yes.
And like what the zone thing you were mentioning before is also like a good solution.
Right. The biggest challenge is blending different manufacturers without having done the pre-testing to make sure that they can play well together. And then if again, everything that we do is a choice. We choose a camera, we choose lights, we have our go-to lights, our go-to system. And the more you can narrow the variances, the less you are battling your post-production issues, and the more you're able to concentrate more on the creativity of lamp placement, shadow, balance, all those things, without having to worry about, well, is this color going to hold up, or is it going to fall apart, or what's going to bite me when I'm least expecting it to.
Sure. Thanks. Awesome presentation. And finally, after years.
You're very kind. Thank you. Frida, I think your last point was a really good one that I've found in my own experience is, that mixing of different light sources can lead you into all sorts of problems. But quite often, I know I do it, but I'm using ones that I know. So they may not be perfect, but I know where the problems are going to be, and I usually know how to get around them. But the work that I find myself doing these days often involves theatrical productions, and they aren't choosing their light sources in that way. And just in the middle of a show, you suddenly see a strange color come up on stage on camera, which you just don't see by eye. And it's a problem that never used to exist before LEDs came along, certainly not in the same scale.
No, and again, because it's about the spectral distribution of that color. We've always had subtractive color generation. We had our gel rolls, we had all our color changers, all those things, and it was all predictable, and it was consistent. And this is why I was said in the very opening of the presentation, this is the first time in history we're expected to work with a light source that is not necessarily harmonized to the recording technology. In fact, it's in opposition at times, and yet we're expected to deliver the goods and make it look fabulous.
Excuse me if I may. I use a very, very weak analogy, but here's what a camera can see, right? And I'm going to send it some light. Excuse me. I'm going to send it some light, and if I send it that light, well, maybe we can see that, Right. But if I send it that light there, maybe the camera can't see that.
That's exactly right.
But is actually sending that light there, so. This light, that's one light, that's another light. So we've got the same sensors, but it's seeing different things from different lights. That's how I kind of think of it, you know.
Well, that's where that's why looking at the response curves of the cameras, you can actually see that. You see how those, how your little valleys differ.
Yeah. How do we speak to Martians? You know, do they see, or do they smell, or do they hear, or do they have a different kind of sense? You know.
I think we'll deal with the LEDs first. We'll worry about the Martians after.
You use the analogy of nuclear submarine commanders. What does a blue whale see, and what should sonar see? Because effectively, all you're seeing is water if it's the same medium. But I digress.
We can't see you, Mike, but we can hear you.
It's probably
whale.
Well, look, am I getting a sense that we've kind of got through everything? I'm sure questions could go on all night, but
there's one last question. There's one last question that I haven't asked, and that was here for quite some while. So, Femi from Nigeria, and I think you partly answered that, but what are the challenges you have come across in relation to skin tone and light?
Well, skin tones have a different absorption, like wavelength absorption characteristics, and this is cross spectrum, various skin tones, and we have the same phenomenon on film. As an example, I remember we had, when we were doing, gosh, well, doesn't matter what film it was. It was a film where we had an actress that had it was a Caucasian skin tone, yet when we photographed her, she had a mustache. She had coloration around here, yet nobody could see it. We looked at it, and makeup didn't even know what to make of this thing, yet there it was on camera. And all I can do is say that there must be certain skin pigments that absorb light differently and reflect that differently to the camera. So depending, again, on the camera response curves, they're going to render that a little differently. So all of this brings it back to what I'm saying in the conclusion. It's all about testing. We're dealing with a technology where we've got two variables. We have a light source that has embedded color science. It has a limited spectrum. It could be different between manufacturers. We have a camera that only sees certain wavelengths, and there are going to be certain things that it cannot render. So when it comes to a skin tone, certain subtleties, certain wavelengths may fall into that zone where the recording technology is challenged in trying to reproduce that. Or it does reproduce it in a way, when you look at it, you go, oh, it doesn't look anything like that in real life. So now the trick is, what do you do to correct it? And that's where you just need some time to do the camera tests and play with filters and try to resolve it. There's no one meter that can tell you exactly what to do, but it does take time in pre-production to try to resolve those challenges.
Yeah, I'd like to throw into that an issue which I have, which is nothing to do with color rendition, but I sometimes think that the gamma system that certainly we meet on television cameras is geared up for one flesh tone. It doesn't work for all flesh tones. It's, you know, the typical problem, you have three people in a panel sitting alongside, and you can't put one light at the right level for all three if you've got one black face, one suntanned face, and one person who's lived near the North Pole all their life. They want three separate keys because the contrast range doesn't resolve them properly, which is disappointing. It's something we have to deal with.
Well, those technical issues, at least I think they're becoming less of an issue, at least within the cinema camera world, because we're seeing those cameras do have a phenomenal contrast range now. If anything, it's so broad, you're trying to actually compress it, bring it back down. Because I think we've, over the years, historically developed a visual language, a cinema language, where we like to sometimes see windows that are blown out. On these new cameras, it's really hard to blow out a window. You've really got to jam an awful lot of light through it to get that thing to go to white. And same with shadow details. when we're shooting film, we always, I did the Ansel Adams zone system of sort of exposure range determination. We always did a camera test where we could see where we would lose highlight detail on a reflected surface and where we would lose shadow detail. And so I knew that was my range of exposure. When I compare that now to an electronic cinema camera, oh my God, it's like a factor of 3. And so now, but we've come used to a certain contrast, a certain visual style. And this is where having the camera LUTs and whatnot comes in play, where you say now, well, from an aesthetic, I don't want the camera to be able to see all that detail. Granted, we're shooting in RAW and all that things, but still later on in post, you're going to bring it down and you're going to compress all that. So these are the fun advantage, the fun things we have to deal with now in electronic cinema world. We have to be conscious of our workflow from beginning to end. And now we're finding that, productions are being asked to master in both 709 and 2020. So which one plays the dominant role? Do you realize more saturation and more vibrant colors in 2020 than you do in 709? So now you're compromising 709. Or do you just keep it in 709 and go, well, yeah, we'll just remaster it in 2020 and it's going to look like 709 anyway. So it's a dilemma.
One of the problems that you can have with when you're trying to match in antique furniture with something which a designer's put into a set, he's dyed it to the eye perfectly, but the response on the camera is totally different. And Kodak used to call it subject failure. And so you've actually got 3 variables. You've got the camera, the light, and what the reflective surface is.
Absolutely, absolutely, yeah. Like I said, you saw the response curves of the film. There were certain colors that just went to mud. You just couldn't do anything with it.
Interesting. Are we, Alexander, are we at the end of the questions now? I think we might be. There's a lot of, in the chat, there's a lot of nice comments coming back about how much they've appreciated the talk, Frida, and I would wholeheartedly endorse that. It's very generous for you to share this knowledge and experience with us. And it's been absolutely fascinating. As I say, I'm looking forward to watching it again so that I can get a bit more of the technical detail out of it, because there's just so much of it packed into an hour and a half. But
yeah.
Very much appreciated. Lovely to see you again, and thank you very much for everybody for giving the talk.
And thank you for your kind invitation. And I wish everyone continued good health. Stay well. Get your shots when you get them. When you can get them. I got mine on Friday.
I got mine last week.
Yeah. Calling it now the geezer shot. I'm at it. Finally, something better than just getting a discount at the museums. You can get a shot.
A very quick bit of housekeeping for the STLD members still with us. We've got our AGM coming up on the 26th of February. So do join us for that. That will be more than just a few people sitting in voting the next committee in. So hopefully that'll be a nice social evening. And also a week after that, we've got Dave Davey, who is the lighting director for Dancing on Ice, with his 2 programmers, going to give a talk mostly aimed at students, but I'm sure a lot of people will find that interesting. So he's hosting a Zoom talk, talking about how he does the program and asking any questions about, if people wanted to know how the show's put together. So that should be a great evening. So thank you very much, to Frida and to Kino Flo and to Cirro-Lite for enabling the meeting. Thanks, everybody.
Stay well. Stay well.
Stay well. Stay safe.
Bye now.
Thanks.
All right. Cheers.
Cheers.